When we last talked about space as a warfighting domain, our focus was primarily on anti-satellite systems. But if that episode focused on what you, lowly Earthling, could do to space, today I want to focus more on what space can do for or to you, and why nations may have more incentive than ever to be able to put a lot of stuff up there. Because while we're not quite yet at the point of commanders being able to call down ion cannon strikes or orbital bombardments, the development of new sensor and communication technologies have made satellites ever more indispensable in both civil and military affairs. And with the emergence of new constellation-based systems, the number of satellites in Earth orbit has exploded. But in order to take advantage of the potential of orbital assets, you need the ability to get them there in the first place, and to do so in much greater quantities than ever before. That's driven something of a good old-fashioned space race to build more and better rockets. And while different powers have seen their positions rise and fall, the United States has launched itself further and further into the lead. First with dominant systems like the SpaceX Falcon 9, and now potentially with the latest test of the super heavy Starship launching system, which, if it eventually performs as promised, won't so much shift the cost curve on getting mass into orbit as thoroughly break it. So today I want to talk about why there's such a push to get more and more satellites into orbit, and why the launch market has gone from looking like this in 2013 to this in 2024. To do that, I'm going to work through a couple of points in sequence, starting with the changing value of the space domain in terms of technology and also the Constellation Revolution, when more and more we're seeing a reliance on vast numbers of smaller satellites in lower orbits rather than a few large expensive ones much higher up. That'll explain why the second part of the discussion is so important, the capacity of different countries to lift material into orbit. There, we'll look at a couple of major players, Russia, Europe and China, but also really zoom in on a country, indeed a company, that's been able to make space travel almost routine, with a look at the technology and business model behind SpaceX and Starlink. Finally, given how quickly all this is changing, we'll close out with a quick look at some of the major developments that might be in the pipeline. Okay, so to start with, I think we need to talk about why nations might be so keen to get a presence in space in the first place. To go back to just some principles of competition 101, the importance of dominating a given domain, say the air or cyberspace, is closely related to the sort of value that domain can give you or an opponent. Having air dominance in an era where the most advanced human flying machine is a kite or a balloon is somewhat different in terms of value to air dominance in an era of precision-guided munitions and atomic weapons. In a sense, you could argue that same logic applies to the space domain, where as technology has improved, the value of you having a good space program while your opponent doesn't has become more and more relevant to the overall military and political balance. A classic example here would be in the field of reconnaissance, aka spy satellites. For as long as they've existed, they've always given the countries operating them the ability to gather some degree of information on their competitors. But just how much information can be gathered and how quickly it can be recovered, analysed and acted on has changed significantly. Some of the first optical spy satellites didn't actually have the capacity to beam their images back to Earth. Instead, they would take photographs on physical film, eject that film out of the spacecraft, and then hope against all hopes that it was going to be the good guys recovering the payload when it fell to Earth, hopefully in the right spot. No matter how slow your modern internet connection is, it probably still has a bit of a speed and flexibility advantage over literal space mail. Cut to the 21st century and there are much more advanced sensor options available. In our episode on submarines, we talked about the potential of LiDAR and its use for terrain mapping. But another major area of advancement, and a personal favourite of mine, has been synthetic aperture radar. From a grossly oversimplified technical perspective, what SAR allows you to do is grab multiple acquisitions from a relatively short antenna in order to achieve the spatial resolution you'd normally get with a much larger antenna. Without SAR, if you were operating a C-band radar in space and wanted a still relatively large spatial resolution of 10 metres, you need a radar antenna a bit over 4 kilometres long. SAR lets you do it without giving every satellite a horrendously long pokey bit. But from a user perspective, satellite-based synthetic aperture radar allows you to do a huge array of things. You can map areas, do change monitoring, biomass assessment. X-band stuff can be pretty good for urban monitoring. And importantly, in most cases, it's not going to give a shit about cloud cover, which can be handy for cutting down revisit requirements or situations where you pay top dollar for some custom satellite imagery, only to, through no fault of the satellite operator, be greeted with an image that gives you relatively few opportunities to inspect stored Russian military equipment, but plenty of chances to admire the finest in Siberian cloud cover. Presumably, in the era of synthetic aperture radar, the absolutely miserable weather of places like Scotland will no longer come with the significant side benefit of providing a degree of cover against orbital reconnaissance. And as well as improved sensors that allow satellites to better gather information, we've also seen leaps in both data transfer and data processing, meaning it is easier than ever to get that data back to Earth and convert it into useful, actionable intelligence. That has implications not just for things like satellite reconnaissance, but also, for example, missile warning. And as satellites and the supporting infrastructure are becoming more numerous and more capable, militaries have become increasingly reliant on them. For most militaries out there that have graduated past smoke signals and allowing troops to bring their own phones, satellites provide an important part of the communication backbone, especially at things like the theatre level. And with the modern military fashion in many places being to connect all the things all the time, we've seen some significant examples of the role of the satellite potentially broadening. And in Ukraine, satellite broadband internet services like Starlink have often been one of the key factors holding the networked battlefield together. We're also living in an era where just about everything, from precision-guided munitions to ships at sea to civilian drivers on city roads, rely on satellites to provide guidance and navigation. There are probably drivers out there that would take their cars straight into the river if the nice GPS lady told them to. And as we've seen reported in Ukraine, sometimes supposedly smart weapon systems aren't that much smarter. GNS denial has severely limited the accuracy of weapon systems like Excalibur, normally capable of pinpoint accuracy. And while there are a lot of different solutions to that problem being invested in or incorporated into weapon systems, a lot of solutions are just focused on making satellite navigation harder to jam or interfere with a classic example being the Iranian Shahed drones that have multiple GNS receivers pinging different networks. The point is that a lot of the spectacle, a lot of the reality of the revolution in military affairs that we saw in the 1990s comes down to satellite-based capabilities. Satellite systems help inform the gathering of information, the dissemination of that information across a networked force, and that have often helped enable the kind of affordable precision that has turned information into burning tanks and battlefield effects. And it's not just the technology on satellites that's evolving, it's the approach to satellites themselves, with the rise of the low Earth orbit constellations. In the past, a lot of satellite functions have often relied on putting relatively expensive, relatively large satellites out in relatively high orbits, as opposed to the increasingly popular low Earth orbit constellation approach of satellites that are smaller, cheaper, much more numerous, and in much lower orbit. And I do mean much lower and much cheaper than some of the important legacy assets that are out there. America's older Milstar communication satellites, for example, reportedly weigh about 4.5 tons each, and adjusted for inflation, likely cost well over $1 billion per in 2024 dollar terms. And they sit out in a geosynchronous orbit, something like 22,000 miles above the Earth's surface. Sitting out in that orbit does give you some advantages. Each satellite has line of sight over a relatively large portion of the Earth, and so you can reliably achieve global coverage using relatively few individual platforms. Between 2008 and 2019, for example, the Japanese operated their wideband internetworking engineering test and demonstration satellite, aka WINS. It provided satellite internet to Japanese customers and was able to do that using only one satellite because it was in a geostationary orbit. From the point of view of a customer in Japan, the satellite would always be overhead and able to beam in signal. But newer satellite internet and communication systems have often instead started to rely on constellations, swarms of much smaller and cheaper satellites in much lower orbits. Instantly, what that might let you do are address the dual problems of bandwidth and latency. These are both metrics related to data transfer, so they're going to be especially important for uses like communication. Your bandwidth is essentially how much data you can push through your connection in a given unit time. And so far it seems that swarms of cheaper LEO satellites are the more efficient way to create it. But an even clearer advantage of the low Earth orbit constellation concept, just from a raw physics perspective, is when you start to talk about latency. When you're using a satellite communication system that's in a geo orbit, a ground station can be exchanging information with it at the speed of a radio wave. That's very fast, but remember those geo orbits are roughly 22,000 miles away, meaning that unless you can rewrite the fundamental laws of the universe itself, you're going to have to bake in a roughly 120 millisecond delay each way. And that's assuming there are no other sources of latency in your system and that one exchange of information is all you need to get a given result. In a lot of contexts, pinging 800 or 900 might not matter. A 1 second delay is going to look very different if you're sending text messages as opposed to playing a first-person shooter and rubber banding all over the place. But you can imagine plenty of scenarios where it would really matter in a military context. We've seen videos out of Ukraine recently, for example, of FPV drones being used by operators to shoot down other drones. The bandwidth requirement there isn't massive, it's low-resolution video coupled with some control signals. But good luck hitting one small flying object with another small flying object if the video you're getting is a second out of date, and it takes another second again for the drone to receive your instructions. In theory, a low-orbit constellation can avoid that problem. And there are plenty of signs that major players are aware of the potential advantages here. To quote one Army publication, the Army relies heavily on geosynchronous Earth orbit satellites, which are fixed in the sky and easy to track, yet the high orbit distance delays communication and requires significant power when transmitting data from the ground to the satellite. Incorporating other satellite constellations, such as low Earth orbit and mid-Earth orbit, with their different ranges and capabilities, allows the Army to obtain the resiliency and diversity it needs to ensure consistent, beyond line-of-sight communication in a variety of battlefield environments. Employing constellation-based sensors also has some potential advantages. Revisit time, that is, how long it is until you can look at something again, is obviously going to be less of a problem if you have thousands of satellites passing over an area, as opposed to just one or two. But there's also some very cool, unique things you might be able to do if you can point multiple sensors at the same rough location at the same time. We've seen some reporting around the US Defense Advanced Research Projects Agency, the famous DARPA, issue contracts for capabilities and research into having multiple synthetic aperture radar satellites pass over a target in formation, then using advanced processing to fuse that imagery and generate additional insight. At a wider level, we've seen DARPA start to use the concept of mosaic warfare. And while that's a bit of a brain stretcher of a concept that we'll get into another time, for now it's enough to say that this sort of satellite reconnaissance wizardry is exactly the sort of thing the concept might call for. But one of the biggest differentiators for these large constellations of hundreds, thousands, or tens of thousands of low Earth orbit satellites is the way they might address the problem of survivability and redundancy. During a war, you usually don't want your opponent to be allowed to have nice things. If space-based assets are important, it's logical to assume a competitor might try to destroy or degrade them. We talked about anti-satellite weapons on our first video on this topic, and recently there's been continued reporting around the idea that Russia may have launched an anti-satellite weapon into orbit. Admittedly, reaching targets in medium or high orbits is going to be more expensive and more difficult, but if there are only a handful of targets, it might be viable. By contrast, with an LEO constellation, there is no single golden target. Destroy 1, 2, or 15 satellites in a constellation, and the load and task can be redistributed among the remainder. This is basically the complete inverse of the classic sci-fi trope where every bad guy has to have a single mothership, control ship, or other single point of failure. I mean, personally, I would love to meet that Trade Federation procurement officer who signed off on a droid control program where one kid in a starfighter who never passed flight school can destroy your entire planetary invasion plan by taking a particularly lucky shot at your one weak point. In the real world, most militaries are likely to take at least some issue with a system designed that way. And if you do have potentially vital functions relying on a couple of large expensive satellites, you better have a plan for making sure that they stay there and stay safe. A large constellation approach, by contrast, can take a bit more of a Lord Farquaad approach to the whole thing. You don't necessarily need to bother investing in defending individual satellites because losses and attrition are to be expected. I'm reminded of that incident back in February 2022 when SpaceX lost 40 Starlink satellites in a single incident to a geomagnetic storm. The public response was basically a quick shrug before more launches and more satellites were sent up to replace them. And if you flip this around and look at it from an adversary perspective, poking a viable hole in a large constellation is going to be potentially very, very daunting and extremely expensive. Most existing kinetic anti-satellite weapons are not exactly cheap and available in only relatively small quantities. An SM-3 missile goes for north of $10 million per shot, which might be a bargain if you're shooting at a satellite that cost $250 million to put up there, but probably not if you're shooting at mini-sats that are bussed up there by the dozen. And while you might be able to embrace more costly, devastating, high collateral damage anti-satellite options, for example, setting off a nuke up there or creating so much orbital debris that you experience Kessler syndrome, those approaches are likely to come with serious drawbacks like taking out your satellites as well, forcing you to fight in the proverbial shade, the potential diplomatic impacts of wiping out a bunch of neutral and allied satellites, and after all is said and done, the risk that your opponent might just try and regenerate their constellation, potentially at a less debris-choked orbit, and dare you to do it all again. All of those factors combined might increase the odds that an opponent is deterred from ever taking a shot in the first place. leaving you to enjoy the benefits of your space-based assets in relative peace. So what I want to do here is give a sense of the speed and scale with which satellite constellations have been growing, noting that in part this might be because of increased demand, but also because there's only so much real estate at play, both in terms of physical orbital space and also sections of the spectrum for those satellites to operate on. If you operate a satellite broadband service, for example, and get licensed to operate on part of the spectrum, it's often going to be a use it or lose it situation. Governments and organisations don't tend to take kindly to electromagnetic squatting. So if you stake out some orbital or electromagnetic turf, you better be ready to get your hardware in position. That note in place, there's a couple of major satellite constellations out there. Previously, some of the more numerous groups of satellites in further orbits were GNS satellites. Each of the space superpower blocks, so to speak, tend to have their own satellite navigation system. In part, one imagines, because it wouldn't be great if your competitor could deny you access to satellite navigation whenever they felt like it. There's the US government-owned Global Positioning System with just north of 30 operational satellites, the Russian GLONASS with 26, the European Galileo with closer to 30, although not all of them are active at any given time, and the Chinese Beidou, which has grown significantly both in terms of satellite and ground infrastructure and may actually now be the most capable of those systems in certain parts of the world. All of those strategically significant objects tend to hang out in medium Earth orbits, continually beaming signals down to the Earth's surface, whether it's to help an Uber driver find a pickup point or a JDAM find an ammo depot. But in terms of raw number of satellites, these MEO constellations have been massively outgrown by low Earth orbit ones, primarily involved in providing broadband internet. And in something of a recurring pattern, different programs tend to have different nation-states behind or backing them. OneWeb, for example, is a low Earth orbit internet providing constellation that primarily works with businesses, governments, telecommunication networks, rather than individual customers. And if you look at the ownership and investment structure of the two main constellations we're going to look at, this is the less American one. There have been investments and ownership interests originating from Korea, Japan, India, France, and the UK government, which still retains a golden share and veto over some matters. The American-based Starlink so far has followed something of a different business model. They sell terminals and services directly to consumers, whether that be because you're in a rural area with dogshit internet access and want something better, or, as we've talked about on the channel, you're in a place like Ukraine where the Russians can blast apart the telecommunications infrastructure, but they can't target the American-owned satellites. And so Starlink terminals supplied by volunteers or allied governments can provide a critical backbone to Ukrainian networking and communication capabilities. And if you want a slight clue as to how useful they've been, we've got evidence both of the Russians attempting to get their hands on and use terminals themselves, while also dedicating significant resources to trying to jam or interfere with the Ukrainian usage. Earlier this year, SpaceX said Starlink was now connecting more than 3 million people, and you can partly see that reflected in the insane growth of the number of satellites they put in orbit. In 2018, there were no Starlink satellites in orbit. In 2020, fewer than 1,000, and at time of recording, more than 6,000. Meaning they now account for a pretty clear majority of all active artificial satellites in Earth orbit. And while Starlink has been the first of these networks to scale, others have ambitions to follow. Amazon has Kuiper, for example, and both Russia and China are publicly discussing their own potential Starlink alternatives. And while the constellations we've seen so far have usually been nominally civilian infrastructure with dual-use military potential, there are plenty of signs going forward that militaries and intelligence agencies see the potential here. It's reported, for example, that SpaceX has a contract with the National Reconnaissance Office in the United States to build a so-called Star Shield network, one which is presumably more expensive per unit than the civilian equivalent, but better suited for government requirements and where the government has a greater degree of control. And as for the development of military-centric constellations in Russia or China, well, in some cases there, the dividing line between military and civilian infrastructure is about as easy to spot as a polar bear in a snowstorm. But this global ambition for larger and larger constellations, for everything from civilian communications to military reconnaissance, missile warning, and support of secure data links, all points towards one thing: an incentive to lift far, far more satellites to orbit than humanity has done in the past. Given limitations like line of sight, there's always going to be a practical flaw on how small you can make an effective LEO constellation, and the greater degree of applicable drag at lower orbits has its implications, both positive and negative. On the plus side, lower orbits are to an extent self-cleaning. In medium or high orbits, any debris we put up there is likely to stay there for a very, very long time. While in much lower orbits, you might be talking about decay times measured in months or a handful of years. The downside, however, is that atmospheric drag can't tell the difference between a piece of space junk and a functioning satellite. So eventually, unless new energy can be continuously added to the system, LEO satellites are going to experience orbital decay and burn up in the Earth's atmosphere. That means you might be replacing the satellites in your constellation every 5 years or so. So we're talking about hundreds, thousands, or tens of thousands of units per constellation that need to be hefted up into orbit and then steadily replaced. That probably means countries are going to be incentivized to have enough capacity to launch at the scale they want and to do so as cost effectively as possible. When it comes to working out the cost of lift capacity, there are multiple measures in use. And within those measures, often different ways to calculate them. Some common metrics, for example, include the cost of lifting a kilo or pound of material into a given orbit, which might be an important macro measure if you're trying to launch lots and lots of stuff. And so mark this as the point where we're starting the leaderboard, which will carry through the rest of the episode, with my metric of choice here being the cost in US dollars to lift a kilogram of mass into low Earth orbit. Total cost per launch is another one that can matter because, as far as I'm aware, engineers have not gotten to the point where they can successfully launch half a rocket. And so if you want to put up a payload that only takes up half a rocket's capacity, I hope you can either find another customer to share with you, or you're booking the whole rocket anyway. If you have a small satellite you want to get into orbit, for example, you can go to the SpaceX website, tell them what orbit you want to get to, when you want to get there, and the mass of your payload, and they'll generate a cost estimate for what is basically the space equivalent of Uber Pool. As a final example, you might also be concerned as what the total lift mass of a given launch system is. Because even if, hypothetically, someone came up with an ultra-cheap, ultra-efficient, very small rocket system, that wouldn't help if you were trying to do something incredibly important that involved launching a very heavy or oversized bit of cargo, like setting up a new module for a space station or firing a car at the sun. Beyond cost, there are other things governments and customers might care about when it comes to launch capacity. Availability, that is, can you get a slot in general, can obviously be a concern in a market where demand can sometimes outstrip supply, but national security clients in particular might also care about responsiveness. The reasoning here is that if you have some kind of emergency and you have to put up a new or replacement reconnaissance or communications satellite, for example, you probably don't want the launch provider to tell you the troops will just have to make do until the next slot opens up in 3 to 4 months. So what we've seen in the US, for example, is Space Force invest in building up a capacity for relatively short notice launches, working towards what's been described as a responsive space launch capacity as soon as 2026. We've seen reporting on 2 distinct Space Force efforts, Victus Nox and Victus Haze. Victus Nox is the more premium, more in-house option. The Victus Nox test mission was carried out in the latter part of 2023. A team successfully moved the payload from a factory to the launch site and got it through the payload processing and testing phase within 57 hours. Launch took place within 27 hours of a no-notice launch order being given, and once in orbit, the initialization phase was carried out within 37 hours. It demonstrated, to quote the US Space Force Chief of Space Operations, a mission that went, quote, from the warehouse to on-orbit capability in a week. That's tactically responsive, end quote. So with that understanding of what governments might want out of their launch capacity and the stakes behind it, I want to have a look at the rocket technology race and efforts to dominate this new domain, by looking both at space powers that are having something of a hard time, like Russia and Europe, and those that have been on the rise, like the USA and China. And for this section, I do want to bring a bit of history in for the main actors, because I think it helps put their evolution and recent developments into better perspective. And until recently, it was the Russians who weren't just the kings of tossing turrets, but also tonnage in general into Earth orbit. Much is often made of the fact that the Russians, like the Americans, did their best to pick apart the German rocketry program at the end of the Second World War. And yes, the first ballistic missile fielded by the Soviet Union did look suspiciously like a V2, but everyone has to start somewhere, and often that somewhere is copying someone else. For example, here's an image of the American Republic IV JB-2 flying bomb and a German V-1 flying bomb. Obviously completely distinct systems with no homework copying involved. Very quickly after the end of the Second World War, though, the Soviets would race past the maximum achievements of the German programs, aided by some extremely talented designers and engineers who would first work on a long-range missile program which would evolve into a space program. Although it's worth reflecting for a moment how relatively small historical changes might have led to different results. We spoke last episode about how the Russian Empire lost a number of talented designers after the revolutions. That would include people like Sikorsky and Kartveli, who would go on to be major factors in US aviation development. But in rocketry at least, the Soviet Union was able to hang on to some of its greatest talent, albeit just. Perhaps the most famous and influential figure in Soviet rocket development was the so-called chief designer himself. That is, Sergei Pavlovich Korolev. He was born in what is now Ukraine, and there were a few factors that made his childhood more rocky than some. His parents would divorce, while he experienced war, revolution, and hunger. He made it through regardless and would make a number of valuable technical contributions until he was arrested in the late 1930s and reportedly tortured until he confessed, and sent for a period to a gulag in eastern Siberia, where he sustained a number of injuries, lost many of his teeth to scurvy, and very potentially could have died there, unknown and unremembered, like thousands of the other inmates. However, in part because of the intervention of an old mentor and another famous name in Soviet design, Andrei Tupolev, he was instead transferred in late 1940 to a prison specifically for scientists and engineers, where they could carry on their trade while in prison. These prisoners with jobs would work in accordance with government directives, and after World War II, rockets were pretty high up Stalin's priority list. He would be allowed out of prison in the mid-1940s, but the charges wouldn't be dropped until 1957, by which point he'd already been given a senior military rank, a number of medals and awards, while still technically being a convicted criminal. Under Korolev's direction, the Soviet rocketry program would produce the world's first true intercontinental ballistic missile, the R-7, NATO reporting name SS-6 Sapwood. As an intercontinental ballistic missile, R-7 worked, it just wasn't very good, especially compared to systems that would come later. It was expensive, bulky, took something like 20 hours to fuel, given its cryogenic fuel, and had a standard deviation from its target that could be measured in kilometres. But in designing a fairly meh ICBM, Korolev and team had accidentally on purpose designed the basis of an excellent expendable launch vehicle. R-7 derivatives would put Sputnik into orbit in 1957 and then be modified into the Vostok and later Soyuz launch systems. The Soviet Union would produce these things at significant scale, meaning that after the Soviet Union fell, Russia would inherit not just a lot of rockets, but a lot of rocket industry. The availability, reliability and affordability of Soviet-turned-Russian systems like Soyuz and Proton made the Russian Federation an absolutely top-tier player in the launch market. Indeed, it got to the point where there were 2 times in recent memory where the US became almost entirely dependent on Russia to furnish it with manned space launches. Within the wider rocket family, crew-rated systems are something of a rarity. Governments might be willing to accept a relatively high rocket failure rate if all it's going to be doing is hefting satellites. Losing a crew, however, is something different, and so relatively few rockets are able to achieve a crew rating. After the disaster with the Space Shuttle Columbia back in 2003, NASA was entirely dependent on Russia to carry astronauts to the International Space Station for the better part of 3 years, while the shuttle program was on hold. Then, when the shuttles were retired entirely in 2010 and the program for a replacement crew-rated launcher was delayed significantly, the US would again have to outsource the job of launching American astronauts into space to Roscosmos, even after the Russian annexation of Crimea in 2014. The dependency actually went even deeper than the dependence on Soyuz for manned missions. America's own Atlas V rocket, which was originally designed by Lockheed Martin, first launched in 2002 and still active today, although being phased out, actually uses Russian engines in its critical first stage, meaning more than a few classified NRO payloads, for example, have probably gone into orbit with the assistance of Russian technology. So the strength of the Russian legacy there in terms of rocket design, manufacturing and operation was clearly evident. And going forward, the evidence suggests that Roscosmos wasn't planning to rest on its laurels. There was to be a new family of launch vehicles, the Angara, which would replace, along with Soyuz 2, a number of existing Russian launches. And even the existing ones weren't bad from a cost per payload perspective. For illustration purposes, let's add a couple of them to our chart from earlier, linked to the source in the description. And even relying on the older legacy systems, Russia had managed a pretty strong position in the launch market over the previous decade. In terms of estimated cargo mass lifted into orbit, Russia would top the table in 2013, 14, and 15. It would lose the number 1 spot to the United States in 2016 and 17, and then from 2018 onwards, with the occasional exception, it would come in third, behind the US and China. But part of that slippage in position wasn't so much because the mass the Russians were lifting was falling, but rather because what the Americans and Chinese were lifting was increasing. If you break it up into 3-year periods, Russian launch mass actually increased between 2016 to 18 and 2019 to 2021. And indeed, if you look at that roughly decade-plus period, 2021 was actually Russia's best year in terms of launch mass. Then, however, for some strange reason, this largely international export-based industry started to fall off a cliff in 2022 onwards. 2022 launch mass was down about 45% on 2021 levels. A compounding 10% fall followed in 2023, and so far, 2024 looks to be even lower. And this, for me, brings in the great question mark that hovers over Russia's future as a space launch power. Clearly, they're not going to get kicked off the podium entirely, but the pressures are mounting. After February 2022, things have slowly started to get a bit strange for the Russian launch industry. Sanctions, of course, have slowly clicked into place, but going forward, the bigger question might be around customer base. The Europeans, for example, previously bought a steady cadence of Soyuz launches. That seems unlikely going forward. Even more so given the public optics of the whole OneWeb thing. Before the 2022 invasion, a Russian rocket was due to carry more than 30 OneWeb satellites into orbit. The launch was then cancelled, and the Russians would make a series of demands, including the UK government divesting its share of the OneWeb network and receipt of a guarantee that these satellites which it was due to launch would not be used against Russia. That obviously wasn't forthcoming, so the satellites weren't launched, but neither were they given back. Despite them having virtually no value or use to Roscosmos, Russia wouldn't give back the satellites, and OneWeb would subsequently have to make an insurance claim and book a more than $200 million impairment over the whole affair. I somehow doubt most insurance claim forms come with a section for "a foreign government stole my satellites as a result of geopolitical developments," but I imagine it probably did break up the routine for whoever had to process that one. And while in the near term we've often seen more demand for orbital launch spots than there are spots available, something which will probably significantly help Roscosmos in finding a market for any supply that it has, the medium and long-term picture, with less access to foreign technology, foreign capital, and foreign customers, is very much up in the air. It probably doesn't help either that we've seen some zany ideas of how to potentially militarize Russia's civilian space program. Rogozin, for example, is reported to have toyed with the idea of using a civilian rocket to carry a Fab 9000 bomb to attack area targets in Ukraine, a delivery method that would likely be so expensive and imprecise that if you hired Harrison Ford to fly a cargo plane over a location while the entire pitching lineup for the New York Yankees threw hand grenades out the back, it might not be immediately clear what the more cost-effective means of high-explosive delivery was. But the bigger picture concern here is probably the same as with many of Russia's other strategic industries. There are only so many resources to go around, and so many buyers on a very competitive international market. Sanctions and restrictions can all potentially be mitigated, but only if there are the resources there to do it. And this is a field of scientific and economic competition where Russia finds itself up against competitors that are not themselves currently at war and have a lot more resources to play with. And with constellation demand picking up, just as Russia's space program begins to be cut off, it may be that Moscow's decision to invade Ukraine in 2022 ends up costing it some of the prominence it might have had in the future launch market. Whatever the reason for Russia's relative decline, it's clear that in 2024 its former position at the top of the podium has now been fairly decisively displaced by the old Cold War incumbent, the United States. The US was obviously one of the two main protagonists of the Cold War space race. Just like the Soviet program, the Americans benefited from some extraordinary homegrown talent. The likes of Webb and Goddard come to mind here, alongside more than a little bit of more imported know-how. The Soviets may have copied the German V2 rocket, but so did the Americans, and they also ended up with the bloke who designed the thing, Dr. Werner von Braun, to assist the fledgling NASA in the minor and unimportant role of chief rocket engineer for the Apollo program. Having got plenty of practice with previous designs against closer launch targets, like London, his later Saturn V designs would underpin the Apollo program and power the missions that put the first men on the moon. Some of the heat would seemingly go out of the space race after that point. Generally, the Soviets didn't seem to be fans of being in a race they weren't winning anymore, and American governments were generally much less keen to keep setting money on fire in the space program once the primary scientific goal of very publicly dunking on the Soviets had been achieved. But having arguably come up with a number of world beaters during the early and mid-Cold War, NASA's lift capacity entered something of a controversial era with the Space Shuttle program. What the shuttle was meant to be was a reusable launch vehicle for lifting payloads into low Earth orbit. It combined disposable boosters and a fuel tank with a reusable spaceplane section. The idea was for it to launch frequently, safely, and affordably. So of course, it ended up being very expensive, launching infrequently, and giving America two of its most high-profile space disasters, with the loss of Challenger and its crew in 1986, and the Columbia and its crew in 2003. The shuttles did succeed in their goals of being partly reusable, but they required long overhauls and extensive maintenance every time they returned from spaceflight. And depending on what costs you combine, they were either more expensive or significantly more expensive than existing disposable rockets as an option for lifting payload into low Earth orbit. As we mentioned in the Russian section, the program would end in 2011 without an immediately available replacement, leaving for a significant time Washington reliant on Moscow to lift its astronauts into orbit. After the shuttle, it was the rockets of the United Launch Alliance that would clinch most US government contracts. The Boeing-Lockheed Martin joint venture would operate a number of launch systems, including the Atlas series, and as of January this year, the new two-stage Vulcan Centaur launch vehicle. But to be fair, when I'm talking about US dominance of the launch market, I'm kind of papering over the real story here, because the overwhelming majority of American payloads are now carried by a single company. In 2024, it's SpaceX that are the undisputed lords of lift, the princes of payload, that dominate just about any set of statistics you care to look at. The chart on the right there shows total up mass into orbit for Q1 2024 by launch company. And as you can see, it actually requires a breakout box and a different scale to compare the likes of ULA or CAS Space to that massive SpaceX bar at the top. Now, I'm sure there'll be some people in the comments that compare this kind of situation where a single mega corporation can single-handedly compete with various nation-states to some sort of cyberpunk-esque megacorp or that plot from Advanced Warfare where Kevin Spacey's PMC tries to take on the world. But I want you to understand that this situation is entirely different for a range of reasons. For one, in Call of Duty, the corporation loses. Remember this chart I showed you earlier, dividing launch mass by year by country of origin? Yet, just for fun here, let's see what happens if we add the first part of 2024, and instead of nation of origin, let's look at the launching company, ripping out some oddities like the Ariane Space Soyuz launches just to make things a little bit simpler. And there you go, SpaceX going from a relatively minor player back in 2014-15 to a rough majority of in-scope launch mass in 2020, and more than 80% in 2023 and 2024 to date. And remember that growth in market share isn't being secured because everyone else's launches have fallen off a cliff. There are a number of factors at play, like the recent or upcoming retirement of a number of older launch systems, but there are players out there other than SpaceX that are definitely trying to tap the accelerator. But with a launch mass volume that, in this data set, increased by something like 12 times over the 5 years from 2019 to 2023, SpaceX isn't tapping the accelerator, they've been locked into full afterburner for 5 years now. The question with perhaps the most significance to us is how? And to be fair, there's probably a huge range of factors that go into it. Crushing competitive advantages like this one are seldom monocausal, but there's a couple of big ones that are probably worth looking at. The first is that SpaceX bet big and bet early on reusability. On most missions, launches like SpaceX's Falcon 9 rocket will take off like a normal expendable system, release their payload, and then, as you can see on screen there, the booster section will land vertically on a drone landing pad out at sea, at which point it can be recovered and refurbished for another launch. Coming up with a reusable option involves a wide array of trade-offs. You have to make concessions in how the system is designed. You need to set up recovery infrastructure. And because the expendable system is going to need thrust available to recover itself, you can't lift as much payload as you could with an expendable option. But on the other hand, the payoff is that you do get to reuse your boosters. And at time of recording, SpaceX actually has one Falcon 9 booster that has now flown 21 missions. And by betting big and betting early on this sort of capability, SpaceX has arguably helped secure themselves a significant competitive advantage. Go back even a decade, and there were a lot of senior figures in the industry that very much weren't making the same bet. I'll link a video of an Arianespace executive back in 2013 saying that, quote, "Personally, I think reusability is a dream," end quote, also suggesting the market would eventually wake up to the difference between dream and reality, and that of SpaceX, quote, "They're not Superman, whatever they can do, we can do," end quote. Arianespace would bet against reusable technology, opting for a fully expendable rocket in the Ariane 6. And if you want to know how that's looking so far, here's a very approximate payload to orbit chart for 2013 through 23. We'll come back to this again a little later on, but for several years now, Arianespace has arguably been experiencing something of a launcher crisis. Hence something of a potential impetus to produce a reusable system of their own. And in 2023, the Arianespace CEO projected that Europe would introduce a reusable launch vehicle in the 2030s. But I need to stress that the Europeans were far from the only ones taking this approach. For various reasons, other actors like ULA, Roscosmos, and the Chinese were all very cautious about the technology. SpaceX, meanwhile, basically rocked up to the R&D roulette table and bet it all on red for reuse. So that was arguably step one, picking the right technology. Step two, then, was successfully and efficiently developing it. Here there are potential observations to make both about how SpaceX has gone about development and how NASA and the United States government has gone about contracting and supporting it. On the development side, it seems like the maxim was often to fail fast, with rocket after rocket being rapidly sacrificed in the name of iteration. In December 2020, the first high-altitude test of a Starship, the SN8, resulted in a hard landing and explosion. In February 2021, an engine failed to start on SN9, causing it to over-rotate and hit the landing pad. This obviously destroyed the vehicle. SN10 in early March 2021 managed a test flight followed by a hard landing and exploded about 8 minutes after landing. And this would then be followed up with another Starship being lost in late March. But by May, an upgraded version managed the high-altitude test flight and a subsequent soft landing. We'll come back to the story of the testing of a first-stage Super Heavy booster in combination with a Starship upper stage a little later on. But suffice to say, it was similarly rapid, iterative, and at times destructive. There is a broader observation to make here that can be applicable to many governments, militaries, and other organisations. And that is that fear of failure or perceived failure can get in the way of exploiting failure as a tool to achieve success. One can imagine how after the space shuttle disasters, there was probably very little appetite in the space program for anything overly risky. The preference with development programs in space or in any other sectors would often be to dot every I, cross every T, and avoid situations where it might look like you were blowing up taxpayer money in the name of rapid progress. But as SpaceX arguably demonstrated, a rapid sequence of tests that could arguably be described as failures could potentially yield lessons and results. On the contracting and development side, SpaceX was reportedly able to develop Falcon 1 and Falcon 9 considerably cheaper than if they'd been NASA-led programs. SpaceX estimated a development cost for the first version of Falcon 9 at about $300 million US. NASA estimated that it would have cost them $3.6 billion using a traditional cost-plus contracting approach. There's a lot that goes into explaining that gap, but part of the secret in this case might have been not over-prescribing the requirements. In this case, though, NASA didn't really overdo it with the detail. It wasn't quite at the level of drawing a stick-figure rocket with an arrow pointed towards a space station in orbit, but it was much more towards the end of the spectrum where the client simply defined a high-level requirement, cargo transport to a space station, and then left industry to come up with their best possible answers to that requirement. Another aspect to bringing costs down has been vertical integration. All the first-year business and commerce university students out there will know this as the make or buy decision, where just about any firm in just about any business, whenever it needs something, has to make a choice. Do you produce or source that thing internally, or do you outsource it? If you're manufacturing cars, do you make your own tyres, or do you buy them from someone else? On paper, there can be advantages and disadvantages to either model. Buying a product or service in is often going to have lower barriers to entry and much lower upfront capital requirements. If I manufacture laptops or smartphones and decide to buy my processors from Intel or AMD, then I don't need to invest billions or tens of billions of dollars setting up a fabrication plant for those processors. I can just buy them in. It also limits the amount of capital I'm risking. If I don't want the processors anymore, I just stop buying more. I don't now have a massive factory with lots of capital invested in it that turns out to be a potentially stranded asset. Plus, let's be honest, Intel are probably pretty good at building CPUs by now, and so it's going to be pretty challenging for us to come up with something that is cost and quality competitive. The disadvantages to doing so, however, might include cost and control. Control matters because I might not be able to force the company to produce a product customized to my needs, nor might I be able to stop them saying, hey, we don't want to supply you anymore, or that buyer over there has priority. Do it yourself and you can have a much greater degree of control, and you probably don't have to charge yourself a serious profit margin. For their part, SpaceX is all aboard the vertical integration train. They've designed and built their own launch vehicles, their own satellites for the Starlink program, and of course, their own engines, including the by now long-proven SpaceX Merlin engine for the Falcon, Falcon 9 and Falcon Heavy, and the newer Raptor engines which have been tested on Starship. Raptor in particular is interesting, not just because it's designed for easy reuse with relatively little maintenance, but because the fuel is now liquid methane and liquid oxygen, a methyl-ox mix. Methyl-ox is comparatively a much newer technology than liquid hydrogen propulsion for rocket motors, and there's been something of a developmental race to get reliable methyl-ox engines designed and fielded. There are a variety of Methalox engine concepts out there in China, Europe and the United States, and some have already made it into orbit. But SpaceX hopes to achieve a scale with these engines that other producers might struggle to match by using them to power both the first and second stages of the Starship launcher. We'll come back to that in a moment. Okay then, so you've embraced vertical integration. How then do you go about managing some of its traditional pitfalls? You're not just buying from an existing established manufacturer that might be selling their products to multiple buyers. So A, how do you make sure you have the necessary scale to justify the kind of investments you're going to need to make? And B, how do you hedge against potential downturns and gaps in demand? And so what you really need to make the most out of this model is to have a high tempo of launches and a reliable tempo of launches. So you know that as you pump out and refurbish launches, they're going to be put to use. SpaceX so far has come up with a relatively unique model to do that, by essentially becoming their own client and creating their own demand. The key piece of the puzzle here is Starlink. SpaceX is a launch company, a rocket manufacturing company, and also a satellite internet company. And its satellite internet business, which is expected to actually turn a profit in 2024, is dependent on launching thousands and thousands of Starlink satellites into low Earth orbit, and then, once eventually those expire and burn up in the atmosphere, launching more to replace them. In raw tonnage terms, the Starlink constellation is the single most demanding orbital project that humanity has ever launched. That gives SpaceX an enormous amount of base demand, if you like, to work with. But because they're their own customer here, they do have a degree of flexibility over when exactly those satellites launch. And so to an extent, what you might see happen is Starlink launches serve to suck up spare capacity in the system, so to speak. SpaceX can sell its launches on the market like any other launch provider. That's usually going to be great for the firm because presumably they can do it at a tidy profit. In order to be cost competitive and win work, they really only have to be cheaper than the other competitors out there. And that's going to be comparatively easy to do if you're using a better technology than everyone else and doing more launches than everyone else, thus beating your own cost to death with the scale bat. And in the event the market doesn't buy up all the capacity that you've built up, well, instead of scrubbing the launch, eating your fixed costs for no revenue, or trying to fire sale the slot just to get something launched, SpaceX is going to have options like selling the launch to itself at cost in order to heft Starlink satellites. Reportedly, in 2023, SpaceX made about 96 non-Starship launches and aimed to grow that by roughly a casual 50% in 2024. Of those 98 launches, 64 were Starlink related. The remaining 34 covered everyone else. In some circumstances, increasing capacity further in a situation like that might be a dangerous bet. For SpaceX though, as long as there's sufficient demand from the Starlink and Starshield constellations, some of that risk can potentially be mitigated. And when you start to put all of these pieces together, you end up with the foundation of a sort of virtuous cycle on driving down cost per payload. Because you have a rapid and reliable tempo, reusability and vertical integration can pay dividends. Because they're paying dividends and you're achieving economies of scale, you can bring your costs down. When you bring your costs down, you can bring your prices down, and when you bring your prices down, you win more contracts that allow you to generate yet more scale. And while these numbers are always going to be a little rough around the edges, especially when you start talking about the Chinese or Russian jurisdictions, according to one researcher I talked to, this is a very rough picture of what the results look like. To get payload into low Earth orbit on an Ariane 6 or an Atlas V is probably going to cost you about $10,000 per kilo. The new ULA Vulcans might be able to bring that down to $7,000 a kilo, and the medium versions of the Chinese Long March launches, $6,000 per kilo. But by his estimates, a Falcon 9 can get you there for $4,000 a kilo, meaning that even if these American launch vehicles have a significant additional profit margin slapped on top, they can still win the pricing race, provided you have a kind of payload that can take full advantage of that payload capacity. These gaps are not small. And while there are plenty of reasons, including politics, national security, or just launcher availability, that not all customers out there are just going to rush to take up the cheapest option immediately, it does provide some indication of just how clearly the American launcher may have won this developmental round. And even if other providers are eventually able to come up with something that is genuinely competitive with Falcon 9, that may not be enough to even things up for a lot of launch applications. Because this week, we saw another test of a system which takes the idea of scale in orbital launches to a whole new level. This monster launch vehicle stands more than 120 metres tall, masses close to 5,000 tonnes fully loaded, and has the potential to lift some truly insane payloads into orbit. This is the Starship, and we need to talk about what it might signal about launch capacity going forward. Starship as a system is interesting from both a technical and capability perspective. At its most basic, this is a two-stage design, with a super heavy booster and a second stage, the actual Starship itself on top. Both stages are eventually intended to be fully reusable in most launch configurations and share two critical design decisions: the choice of the Raptor engine and stainless steel construction. The Raptor, as we said earlier, is a next-generation Methalox engine that powers both stages. You just put more of them in the booster. It's also one of the world's first full-flow rocket engines, which are notoriously difficult to build but offer higher performance. The Soviets tested a full-flow engine, the RD-270, back in the 1960s, and the Americans funded a demonstrator of the technology in the mid-2000s, but unlike the Raptor, neither of them made it into orbit. Plus, because the same engine is being used for both stages, you can simply scale the production of as many Raptors as possible, rather than having to branch out and invest in two separate production and sustainment lines. That next-generation engine has then been combined with a very previous-generation material in the form of stainless steel. Using steel for a lot of the Starship structure saves considerably on costs, eases maintenance and manufacturing, plus it's a generally very rugged material with good heat tolerance, at the expense of obviously not giving you the kind of weight savings you might be able to achieve with more advanced composite materials. But to an extent, Starship doesn't have to really care about those potential weight savings because it went to the Kerbal Space Program School of Rocket Design. When in doubt, just add more booster. And even without those composite-driven weight savings, an empty Starship might only weigh about 300 tons. That might sound like an awful lot, because it is, but it should probably be kept in perspective against the nearly 3,500 tons of propellant that might be loaded into the first stage alone. Like the vast majority of rocket designs out there, a fully loaded Starship is mostly fuel. And that's sometimes made for some very dramatic destruction during the testing of the integrated system, the upper and lower stage together. A test of the integrated system in April 2023 resulted in a number of engine failures and eventual uncontrolled spin, followed by the destruction of the launch vehicle. SpaceX declared the test a success. Improvements would be made before a new test in November 2023, which resulted in a longer mission duration, but still the loss of the system. Another launch vehicle would be sacrificed in the March of 2024, all of which led, directly or indirectly, to the most recent test this week, where a Starship booster combo made a suborbital flight and managed a controlled soft splashdown for both stages. It wasn't always pretty, with some flap damage for example, but it was an extraordinary leap forward for a system which was tipping over on the landing pad back in 2021. The 2 points here are that Starship is 1, still very much an experimental and in-development system, and 2, that the pace of that development has been very rapid. And if it does achieve reliability and performs anything like its on-paper potential suggests, it has the potential to be every bit as disruptive to the LEO launch market as the original Falcon 9 and Falcon Heavy. To take one of the estimated sets of figures out there, for example, because there are a lot of them, if we look at a January 2024 report by Payload Research, they estimate that Starship would represent a considerable escalation in how much stuff you could take into low Earth orbit on a single launcher, with a Falcon 9 maxing out at 22.8 tons, Falcon Heavy at 63.8 tons, and Starship at between 100 and 150 tons fully reusable, or approximately 250 tons fully expendable. To give you a sense of scale there, the Russian RS-28 Sarmat is described as a super heavy intercontinental ballistic missile, and its entire fueled mass is about 210 tons, meaning that if it could fit, and it couldn't, Starship would actually be able to lift Russia's heaviest intercontinental ballistic missile, fully fueled, into orbit. The other potential game changer here is not just the mass, it's the size of the payload fairing, how bulky a cargo you can carry. A lot of space-based platforms have to be designed with compactness in mind so they can fit on the top of the rockets launching them. For Starship, that payload fairing is meant to be 8 metres in diameter and 22 metres tall, meaning, to quote directly from the report, quote, "The payload bay could comfortably fit 2 fully loaded semi-truck trailers with additional room and weight capacity to spare," end quote. So now you're not just lifting more stuff into orbit, you can also lift much bigger stuff. And those factors together have 2 potentially major implications. Firstly, in terms of cost, if this thing is mass manufactured and is rapidly reusable, this may be the cheapest way humans have ever discovered, short of firing a Javelin missile at a T-72, to send an object into orbit. While initially the report suggests that SpaceX might charge $3,000 per kilo to lift objects on Starship in order to recoup its development costs, The floor price for internal launches of things like Starlink might for the first time ever be measured in hundreds of dollars rather than thousands. If you want to visualise what that looks like, here's a chart from the report on screen now. I don't know exactly what sort of efficiency numbers Starship will realise and when they'll realise them. But the key point here is that if this combination of scale and reusability can be made to work on anything like the scale being promised, you may potentially see more of that self-reinforcing economic cycle we described earlier. Lifting stuff into orbit becomes cheaper, so people want to lift more stuff into orbit. As a result, you can harness more scale in your Starship lifts and drive costs down further. But I think the potential may actually be a little bit deeper than that, both because you're now potentially unlocking low Earth orbit for heavier and bulkier cargoes, but also because of what it might mean for satellite design. Historically, larger space-based platforms have had to pay an immense design premium in order to be as light and compact as possible. As the report notes, the James Webb Space Telescope was originally meant to cost $500 million in 1997 terms, and ended up costing closer to $10 billion. With, according to the report, the primary reason for that being volume and mass constraints, which, quote, continuously compelled engineers to reduce size while maintaining performance, thereby increasing complexity and consequently cost, end quote. But if you tell satellite designers that you can send up something the size of 2 semi-trailers, and their cost per kilogram tax is now an order of magnitude less than what they previously had to deal with, then there might be real possibilities there to economise in terms of the way satellites are designed and built. Cheaper but heavier satellites could mean more demand for lift capacity, and thus even more scale. So arguably, we're already in a situation where Falcon 9 has disrupted the launch market, and a Starship that performed as advertised could potentially turn that competitive gap into a chasm. But almost no matter how things proceed after this week's successful Starship test, I think it's important to stress that the space race is still very much on. And even if they're more than a few laps behind, the other competitors aren't about to call time. For example, if SpaceX wasn't a thing, this video could well have been mostly about the People's Republic of China. As in many other scientific and technical fields, China has been making enormous strides when it comes to space. They've designed new launch vehicles, built up their own satellite navigation system, launched an array of military and civilian satellites, and enabled by those new and modernised launch systems, the amount of mass they've been sending into orbit has rocketed up, to the point where the PRC lifted very approximately 4 times the payload into orbit in 2022 than it had in 2013. And there are 2 additional points that need to be made here. Firstly, even if Chinese launches aren't as economical as the Falcon 9, they might be economical enough. As long as enough resources are allocated, Beijing is likely to be entirely capable of launching large numbers of satellites into orbit. And from a security, political, and industrial policy perspective, it seems incredibly unlikely that Beijing would give up on its own launch industry just to save a few bucks by putting all of its sensitive cargoes on an American company's rockets. It's also the case that innovation can inspire imitation. And while it's still likely many, many years away, we've already seen China show off concepts for what many have described as its Starship, the Long March 9. With a number of features that might sound rather familiar, like a reusable first stage powered by Methalox engines. The Europeans are also not calling it quits so much as redoubling their efforts. As the chief of the ESA reportedly put it, they've been going through something of a launcher crisis in recent years. They've obviously lost access to the Russian Soyuz 2 boosters, and the much-awaited Ariane 6 has been long delayed. Originally slated to make its first flight in 2020, the rocket is now expected to launch for the first time on July 9th this year. When it enters service, Ariane 6 is not going to give the Europeans the most cost-efficient launch system on the market, but they will have a launch system. And given the emphasis placed in many influential European capitals on ideas like strategic autonomy and maintaining the European industrial base, it seems incredibly unlikely they'll just hand all their government contracts over to SpaceX, but instead pay a premium in the short and medium term, and hoping that a reusable Ariane rocket does indeed appear in the 2030s. I could also talk about other increasingly important players in space like India, but by now you probably get the picture. Not everyone who needs something launched is going to go to the cheapest provider, and a lot of governments have an interest in protecting and supporting their own domestic industry and capability. Just as with the purchase of military equipment, for many governments, who you buy your launch services from is a strategic decision, and one where the incentives sometimes line up in favour of paying more for less. India's space program already operates on what, by international standards, are some very tight budgets, and so the opportunity cost probably isn't that high for the government to push on with more domestic options. But I think it's important to understand that there is a significant gap here, in terms of cost and in terms of capacity. And the launch business is one where there are some win-harder mechanics baked into the system. Governments may choose to go with domestic providers for strategic reasons. Companies may be willing to pay a premium to diversify launches across multiple companies in order to mitigate some risks. But as long as the American launchers can regularly offer more for less, they're likely to win, and so far have been winning, a majority of the work out there where price is a driving consideration. And with the virtuous cycle of wins driving scale, driving cost, driving wins, there are likely going to be significant barriers to other providers trying to narrow the gap. But one way or another, I think by now the overall trend is relatively clear. There's more launch capacity than ever before, it's cheaper than ever before, and it may be on the road to getting even cheaper. To zoom out in closing then, I think it's worth asking the question, what happens next? What are the potential implications of this new space race and the proliferation of both constellations and launch capacity? In the near to medium term, the implications from a defence and security perspective are arguably already becoming evident, with significant plans believed to be in place to scale up the number and types of sensors in orbit. We've previously talked about American plans to use satellites to detect incoming hypersonic weapons. And as launch costs continue to come down and technology continues to improve, we may see a high ground that's more and more crowded with military, civilian and mixed-use assets, giving an entirely new level of awareness to analysts and decision makers. With that potential value, of course, comes questions over potential weaponization and military escalation. We've seen calls for further restrictions on the militarization and weaponization of space and space assets, but at the same time, we've often also seen some opposition to those efforts. And if launch costs come down significantly, previously zany and unfeasible ideas might move closer to feasibility. Back in 2003, for example, the US Air Force so-called Transformation Flight Plan touched on a number of ideas along the reasonable to unreasonable spectrum, including so-called hypervelocity rod bundles to defeat anti-access area denial strategies and deny an adversary sanctuary. Basically, you lift giant metal rods into orbit, and then when you need to hit something, you decelerate them and slam your metal rod into the ground at hypersonic velocities. From a technical feasibility and cost perspective, that's pretty out there. But at least on the cost side, how out there it is, in part comes down to payload cost. If you're paying $20,000 per kilo for a 10-ton payload, you're looking at $200 million per shot, plus everything else that goes into making the system work. Cut that cost down to $1,000 per kilo, and suddenly you're talking $20 million. Still a very expensive way to get a long piece of metal somewhere, but not entirely out of spec with some of the more expensive conventional hypersonic weapons we've seen. Note this is not me saying whether this system is a good idea or likely to happen. Instead, I'm just illustrating the kind of pressures that might happen once you start slashing zeros off launch costs. And from a competitive perspective, the impact of those decreasing launch costs and increasing capacity arguably flows both ways, not just pointed towards Earth, but also pointed away from it. A more and cheaper launch capacity goes a long way towards potentially putting more of the rest of the solar system in practical reach, with multiple countries either planning or at least toying with the ideas of manned missions not just to the Moon, but also potentially to Mars. But the potential for geopolitical competition beyond Earth's orbit is very much a topic unto itself, and one we will look at in the next episode of this series. And alright, let me close out with a channel update. The space series that we started some time ago is very close to my heart, and now finally seemed like the right time to continue it. The recent Starship test was fairly dramatic and drew a lot of eyeballs, but the broader revolution in launch capacity, launch cost, reusability, etc. has arguably been going on for some time. And I really hope you enjoyed a chance to look at the evolving picture and its potential implications. I have some broader updates I want to give, but they probably need to wait a week or two while I just confirm a few things. So in the meantime, as always, let me just say thank you for your continued engagement and support, and I hope to see you all next week.